here to talk about. So as has been mentioned, I'm heading up a new National Science Foundation sponsored project called Low Energy Options for Making Water from Wastewater. And just to give you a little bit of context to how this all came about, I have spent most of my career working on dispersion of pathogens and bacteria in coastal waters. And you know, I had a decent time doing that over the years, and then it came time for sabbatical. I had a year to take off and think about doing something different. And I resolved to do two things. I resolved that first, I was going to write at least one paper that did not have the word fecal in the title. And I was going to do the same for a proposal. And so that was kind of the genesis of this UCI Water-PIRE thing. Ended up writing with my colleagues a paper for science, and then this National Science Foundation project for the PIRE. But you'll notice that in the title of both of those, it has the word wastewater, and you might question whether wastewater and fecal are actually very closely related. So I'm thinking these are baby steps, so I'm slowly getting away from fecal over time. But if I wasn't going to think about fecal bacteria or fecal viruses, I had to go somewhere where they don't think about fecal bacteria and fecal viruses. And so I settled on Australia because they're too busy running away from crocodiles and sharks and cassowaries to worry about bacteria in their waters. And in particular, I went to Southeast Australia and Melbourne, which is shown in the star there, which is a city of about 4 million people centered around Port Phillip Bay. And what I found in Melbourne was a population that is absolutely obsessed with water. That's all they can think about. If you get in the taxi cab and you ask how things are going, they're going to tell you all about the water supply system and how they're conserving water and so forth. And that really came about through, as the Dean mentioned, the Millennium Drought. This shows the time series of water inflow to the major reservoirs in Melbourne from early 1900s to pretty much the present, 2012. And you know, there have been ups and downs, a number of droughts along the way, but the average inflow is about 615 gigaliters per year from 1913 to 1996. But then they had a sudden drop for about a 12-year period from 1997 to 2009, which basically halved their inflows to the reservoir. And during that period, things got pretty dire. Their reservoirs started draining, and there was a lot of concern over whether they'd be able to survive. They did a lot of innovative things to survive that drought, and that's really what our project was based on. We wanted to go to Australia to figure out what they did and see if there were lessons for us in the US in general and in Southern California in particular. And so that's the UCI Water-PIRE. It's the genesis of it. What is it? PIRE stands for Partnerships for International Research and Education. It's an NSF-wide program. Basically, it's a competitive program. Astrophysics, biology, genetics, all fields of NSF funds can compete for these funds. The goal of which is to basically partner with an international organization, university, lab, and so forth, and do something innovative for the U.S. Our project is $4.8 million over 5 years. And we have a number of elements. We have undergraduate boot camp. We basically take a bunch of undergrads to Australia to experience field work as well as teach them about water sustainability. We have PhD scholarships, so we're supporting between 7 and 10 of those for research with Australia. Everything has to involve research in Australia. We have 3 postdocs, PhD level folks who are working with our scientists and professors on the project. And we have outreach to water community. We've been partnering with CASQA, the California Stormwater Quality Association. Had a PIRE session at their last annual conference. And next week we'll be presenting 7 talks actually at their workshop on stormwater. And we are also trying to cull all this information, all this research and education activities into K through 12 modules as well. So it really goes the full spectrum from trying to educate old professors like me down to disseminating K through 12 modules. And again, it's very much like we've been hearing. The project is focused on low energy approaches for capturing and treating stormwater. That's a big part of what we're interested in. So I won't go through that since we've already talked about some of those technologies. But here's how the project breaks down in terms of our research. We basically have 4 different research layers that we focus on. We are focusing on pollutant removal and treatment in green infrastructure, public health risks and energy savings and greenhouse gas emissions from these systems, looking at regulations, economic instruments, equity and policy associated with the implementation of these activities, and then also their effect on watershed scale processes. It is a partnership between a number of different institutions. UCI is leading it, but we do partner with our obscure neighbor to the north, UCLA, and our equally obscure neighbor to the south, UC San Diego Scripps Institution of Oceanography. And then, of course, we have our major research partners at the University of Melbourne and at Monash University in Melbourne. And then helping us with outreach is the Southern California Coastal Water Research Project, SQUIRP, which is located in Costa Mesa here. I'm going to highlight just a couple of projects. I'm going to tease you with 2 of them. One involving greenhouse gas emissions from treatment wetlands, which is being spearheaded by one of the postdocs at Scripps, Andrew Merring, and his advisor, Professor Lisa Levin. And then I'm also going to tease you with a little bit of a description of a study we're working on involving virus removal in stormwater biofilters that's being conducted by graduate student Eric Huang with his advisor, Sunny Jiang. And then finally, one of my students is working on a project where she's trying to understand what caused the dramatic reduction in per capita water consumption in Melbourne, Kathleen Lowe, and then that's my smiling face right there. So again, I'm going to just give you a little bit of a teaser on a couple of these. So Andrew is a wetland ecologist, and he studies in particular animals in wetlands. You might not think that there were a lot of animals in wetlands. And we're not talking about big animals. We're actually talking about very, very small animals, things like worms and insects. And it turns out that these wetland systems or biofilter systems, the green infrastructure, can be a haven for these organisms, and they play a role. They have a function. They carry out nutrient transformations. They potentially mobilize nutrients. And his project in particular is based on an observation which was published in the Proceedings of the National Academy of Sciences about a year ago, that the gut of midges, which are these little flies, fly larvae that nest in the wetland systems, actually are like the perfect incubators for producing a very potent greenhouse gas called nitrous oxide. And so his hypothesis is that if these systems are set up in such a way, maybe they're not maintained properly, that they become sort of a magnet for these midges, that they could actually end up generating a lot of greenhouse gas, which would be obviously a problem. And so he's on the, I didn't even know that word, he's on the path toward running a field program this summer in which he's going to be measuring greenhouse gas emission from a number of different wetland and biofilter systems in Melbourne that have essentially various degrees of these midges in them. But more generally, they're very interested, this particular group, in the role that the animals in these systems are playing in terms of their function. Another project, again, just a teaser. So Professor Sunny Jiang is an expert in virus detection and transmission through natural systems. And her student Eric Huang and her are working with Monash University. Monash has a $100 million research center focused on biofilter design. And one of the things they have there is an amazing facility with many, many different combinations of plants and biofilter systems. And so he's taking advantage of that and his own expertise and his advisor's expertise in growing and detecting human adenovirus to look at virus removal in these systems. And this is really important because we'd like to be able to give removal credit to these green infrastructure for human viruses. It's extremely important from a health perspective, but also just from a regulatory perspective and implementation perspective. And so he's collecting some of the first data on live human virus removal in these systems with his advisor. And he's actually in Australia as we speak, working on that. And now let me just transition to a project that one of my students is working on. I'm going to give you a little bit more detail on this, and then I promise I'll let you go because I know you guys have a busy day, although I think we do have a bit of a discussion that's going to occur if you want to stick around. So this is one of my grad students, Kathleen Lowe, is working on this, and it really came out of a paper that my colleagues and I wrote for a feature in environmental science and technology that was published a couple of weeks ago that focused on what happened during the Millennium Drought in Australia. A lot of things happened, but I think this chart tells an amazing story. So what you're looking at is the per capita potable water consumption in liters per person per day in Australia, sort of just about a year before the drought, and then coming into the drought to the present time. And so what you're seeing is a dramatic reduction, almost a 50% reduction in per capita consumption over the period of the Millennium Drought, going from about an annual average of 500 down to closer to below 300, almost 250. This is really quite remarkable, and then the question is, what caused that? So, in summary, we basically observed that Melbourne decreased its per capita potable water consumption by about 46% over 12 years. And you might wonder, well, is that significant or not? That translates in 2012 to a savings of 300 gigaliters of water for Melbourne, annual 300 gigaliters. What does that translate to more locally? We hear a lot about the groundwater replenishment system in Orange County, which is a really wonderful system. That, at maximum, according to their website, would generate 88 gigaliters per year. That's essentially less than 3 times the amount of water that was saved by the reductions that Melbourne put in place. We heard about the LA Aqueduct. 100-year anniversary of the LA Aqueduct brings, according to your website, about 228 gigaliters, so still less than 300 gigaliters that was saved in 2012 by the per capita consumption. The point I want to make here is the extraordinary potential that these reductions can have in terms of reducing the amount of supply that you need to keep your society functioning. Anyway, so the question is, how did Melbourne do it? And you might also realize that the answer to that question is really crucial, because if we plot where LA is, and LA's made a lot of progress in terms of reducing its per capita consumption, but we're essentially now where Melbourne was before the Millennium Drought. So the comment that there's a long ways to go, well, there's the path forward right there. The other thing that I wanted to point out is that if you look at the reductions here in per capita consumption, and you just sort of follow the bottom of the curve, they kind of go in a stair-step fashion. You sort of see that, and then you also see that the amplitude is, so this is higher consumption during the summer, lower consumption during the winter, so the amplitudes are also being reduced over time. So there's a couple of very interesting things going on here. What happened on the ground? Well, there was massive public education campaigns when the Millennium Drought hit. This involved, for example, billboards where they would publish the percent of reservoir capacity on a daily basis. This was on the front page of the newspapers. It was the first thing reported in the news. When I arrived in Melbourne for the first time, I asked a taxi cab driver how the water situation was in Melbourne, and he said 47%. I don't know what that means. And then as we were driving along, but I didn't want to admit I didn't know. As we were driving along, I saw a billboard that said 47%, and so I figured out pretty soon that essentially they had 100% penetration. Everybody was following their water supply situation extremely carefully, and that, I think, was a major factor in the water reductions. They also implemented water use restrictions, which they progressively implemented as they began to run out of water from stage 1 to stage 4. And what's interesting about these is these occurred at very specific times, so we can now look at that per capita consumption graph and go back and try to figure out how much water was saved from each of these interventions. And that's really what I'm getting to. They also had substitution targets, so they ended up recycling 22.8% of their wastewater inflows by 2009-2010, and they also had a very aggressive stormwater and rainwater harvesting program, which by 2010 was accounting for about 3% of the annual municipal demand. They also implemented various water pricing schemes, which essentially signaled the value of the water that was being consumed, and that had an effect as well. So anyway, with all that information, we thought, well, maybe we could extract, again, essentially a sense of what effect each of these policy interventions had in terms of the per capita consumption. And we had kind of a hypothesis that essentially that model would consist of a pre-drought annual average, about 500 liters per person per day. Obviously, there's a seasonal fluctuation. We observed that the amplitude of that seasonal fluctuation is reduced over time. It's actually reduced more than the proportional drop in annual demand. And so we figured that the excess reduction is actually caused by potable substitution, things like wastewater recycling, stormwater harvesting. These are probably permanent reductions. They're not going to elastically jump back again. We also noticed that there are climate effects. If there's more precipitation, obviously you don't need to water your lawn as much, so climate plays a role. And then, of course, we have the policy interventions. And the wonderful thing about these is that they occur over very specific periods of time. So we can look back in that graph and say, what does this period of time tell us in terms of what was accomplished? And just to make a long story short, when we put all these together, so the actual observed per capita consumption is in blue. What we end up pulling out of the data is the predicted. So we do a pretty good job of mimicking a lot of the features of the curve. And what we find is that, well, obviously we can model, of course you can model anything with a polynomial, right? But I mean, with a structured model that specifically takes into account these policy interventions, we can reproduce the observed per capita water demand pretty well. We're now in the process of looking at essentially the fitting parameters, which tell us what they tell us is how much water was saved by each of the policy interventions, which is a very cool result. What does that give us? Well, let's just look retrospectively to assess what worked and what didn't in terms of water savings. And then, of course, it gives us a prospective assessment of what could potentially be applied to other communities around the world, including Southern California. And I just want to emphasize, in case you came away thinking this was a nerdy little engineering thing, which that would characterize me well, but we also, for this project and all of these projects, recognize the importance of interdisciplinary collaboration. And so our demand modeling effort, for example, involves climate scientists, involves economists, involves hydrology folks, ecosystem services folks, and what I didn't mention was that there are also environmental releases that are associated with the water budget in Melbourne, and those are very much tied to streams and stream health. So we're also looking at that, and then governance issues, including with David Feldman. And David's going to say a few words here in a moment. And then I want to finish by just mentioning a little bit about the undergraduate PIRE program. We basically take a bunch of undergrads to Australia, so we pay their tickets and pay essentially full fare for them to stay with us and work their butts off for about a month. But it turns out that people in Stanley want to do that, so we have lots of good applications for doing that. And it's actually a partnership with the department. The department is providing some of the scholarships for the undergrads to go to Australia and participate in this. So when we got to Australia this last summer, which was our first implementation of the undergraduate program, which we call Up, Down, Under, the undergraduate PIRE program Down Under. One of the undergrads pointed out it was actually UPP Down Under, which has a very different connotation, maybe appropriate. But anyway, once we get them there, we took them to 6 field sites, essentially constructed wetlands.